In this video, we're going to derive a simple mathematical model for a subtropical gyre. And it will be simple and very idealized to try to keep the mathematics as simple as possible. So the domain we're going to imagine is a rectangular ocean basin with northward being in the y direction. So this is northward, north. And in this direction, the x variable is eastward, east. And then we'll imagine that we have a square basin to make things easy, or a rectangular basin, where this length scale here is Lx, maybe 3,000 kilometers, and this one is Ly, maybe also 3,000 kilometers. So the ocean basin is here, ocean basin. And if you'll recall, the gyre of the subtropical gyre has a very strong western boundary current flowing northward, and then a return flow, weaker return flow in the interior. So something like this. And this is flowing southward. So the mass flows south in the interior, and there's a sharp and strong western boundary current that returns the mass. And this is driven by a wind field with easterlies at lower latitudes and westerlies in the upper part of the basin. So the wind field we're going to imagine is idealized also, so something like this. Let me make the arrow in the middle, like this. And this axis here, this would be the tau, the x component of the wind stress. So we're going to imagine the wind field is completely in the zonal direction, no north-south wind, just to keep the model simple. So we have westerlies up here in the upper part of the basin, so we'll have the wind going something like this. And this is the wind stress is acting westward and eastward in the southern, in the part of the basin. We're going to approximate this function using a sine function later on. Okay, this is y, and this is wind stress in the x direction. All right, so this is the domain we're going to have, a square domain, or rectangular domain, an idealized wind stress that's purely zonal. And the way we're going to build the model is we're going to assume an ocean basin that is finite depth everywhere. So it'll be an ocean basin, if I try to do a 3D plot, something like this. So this thickness here, we'll pick that to be h, so that's about maybe 4,000 meters roughly, and this here would be Ly, and this direction here is Lx. So it's flat bottom and it's flat at the top. And we're going to assume that there's a rigid lid on the top so that there's no variations in the height of the water as a function of space. Yes, so the first thing we'll start off to make our idealized model is we're going to start with the continuity equation. So the continuity equation, so the mass conservation equation for water, which is a liquid and that's incompressible, is just du dx plus du dy, sorry, dv dy plus dw dz equals 0. So that's the same thing as the divergence of the vector field is equal to this and is equal to 0. In other words, there's no, the flow is non-divergent, so the fluid, you can't squeeze more mass into a volume because water is incompressible to first order. So this is the continuity. We'll take this equation and we're going to integrate it in the vertical over the thickness of the layer everywhere. And we'll only solve for this kind of depth integrated velocity field. So our simple model will have only the description of the horizontal currents, but nothing about the vertical structure of those currents within the ocean. So let's integrate this equation in the vertical to see what we get. So if we integrate this equation, we'll get the integral from the surface, which is at z equals 0, down to the bottom, which is at z equals minus h, of du dx plus du dv, dy plus dw dz. All this integrates back to dz. Now, because the limits of integration here don't depend on x, I can pull the x derivative out of the integral sign for the x and the y derivative, not for the z derivative, but for the z derivative I can just apply the integration and undo this derivative. So what I end up with is d by dx of the integral from z equals 0 to z equals minus h of u dz. So the d by dx of the depth integrated zone eastward current plus d by dy, the integral from z equals 0 to z equals minus h of v dz, plus, and then when I apply the integral on this one, I will just get w at 0 minus w at minus h. Has to be all 0. So this w, that's the vertical component of the velocity at the surface of the ocean, and that's the vertical component of velocity at the bottom of the ocean. So if I was to plot my domain like this is z, and this is the sea surface over here, sea surface, and down here, this is at z equals 0, and is at z equals minus h. This is the ocean floor. What I get is the value of w at the top and the w at the bottom. Now, because the sea surface is assumed flat with a rigid lid, this one has to be 0. Otherwise, the sea surface would be rising or decreasing. So this one is 0 at the surface. And the same thing at the bottom. Because we have a flat bottom, w at the bottom will also be 0. Otherwise, there would be water flowing out through the ocean bottom, which can't happen. So this one is also 0. So these two here are 0, 0. And so what we're left with instead is just a two-dimensional divergence equation for the continuity equation. We just get the following. d by dx of u plus d by dy of v is equal to 0, where these capital u's and v's are the depth integrated currents. So u is defined as the integral from 0 to minus h of u dz, and v is defined as the integral from the surface to the bottom of v dz. So these are these new variables. These capital ones are depth integrated currents. They vary in x and y, but they don't vary in z because the z variable has been integrated out. And we're going to work with these variables to make our simple mathematical model of the gyre, to keep this things as simple as possible. So the next things we need to look at are the momentum equations. And now I'm going to show you how to take the momentum equations, combine them in such a way to get what's called a vorticity equation. And the nice thing about the vorticity equation is that the pressure forces vanish from the vorticity equation, which makes the equation much easier to analyze. So let's work with that. So remember this equation, and the definition of the u and v are these depth integrated currents. Okay, let's write down the momentum equations in the horizontal momentum equation. So we have du dt plus v dot grad u minus f times v is equal to 1 over rho naught dp times dx plus ah del squared h u plus av d2 u dz squared, where del h squared is the horizontal Laplacian, so it's a shorthand notation for this. So the second derivative with respect to x plus the second derivative with respect to y, and that originates from the divergence of the gradient that shows up because of the horizontal eddy stresses, which we parameterize as being down gradient. Okay, and then the horizontal momentum equation, dv dt plus v dot grad v plus f times u is equal to 1 over rho naught dp dy plus ah del squared h of v plus av d2 v dz squared. Okay, and now we're going to make the same approximations we talked about last time. We're going to assume that the ratio of this to this is small, so we can neglect this term in favor of this one, or neglect this one in favor of that one. In other words, we assume that the Rossby number, which is is defined as the velocity scale u over fl is much less than 1. In other words, the magnitude of this term is small compared to that one. In this case here, U is not the depth integrated current, that's just a horizontal velocity scale for the current. So we're going to assume that this is small for the large scale gyre circulation, which is a good assumption. It's true everywhere except maybe when we get in the western boundary currents, then this can start approaching close to 1, a little bit less than 1, but so we would make some considerable errors in the Gulf Stream. Okay, so assume that these vanish. We're going to assume a steady state. Assume a steady state, so that we can neglect du dt and dv dt. Both assume 0. And after that, we're going to take these equations and depth integrate them. Okay, and so that we can use this relationship that we derived before, that the horizontal divergence of the depth integrated currents vanish, provided we have a flat bottom in a rigid lid, which is what we're approximating in this model. This is our approximation. So let's depth integrate these equations. What do we get? We'll get, well, these terms we neglected, so we get minus f. The depth integral of v is just v, capital V, equals 1 over rho naught times the depth integral from 0 to minus h. I will write it out here. 0 to minus h, 1 over rho naught dp dx dz. Yeah, plus ah del squared h u. So I can interchange the vertical integral with this Laplacian operator, because the limits of integration at 0 and minus h are independent of x and y. And so I could take the depth integral inside and get a capital U and plus. And now here, if I do a depth integral, I'll just take away one z derivative, and so I'll evaluate du dz at the top and the bottom of the ocean. So here we would get av du dz at the top, z equals 0 minus av du dz at the bottom of the ocean. And I can do the same thing for the y momentum equation. I get plus fu 0 to minus h 1 over rho naught dp dy dz plus ah del squared v plus av, and again the dv dz at the top and the bottom of the ocean. So this becomes dv dz at z equals 0 minus av du dz, dv dz at z equals minus h at the bottom. Okay, so these are now our depth integrated equations, and we can now use boundary conditions at the top and the bottom of the equations to eliminate these terms. These, remember, these are stress terms, eddy stress terms. If I multiply by rho naught times av du dz, the surface boundary condition is that this is equal to the eastward component of the wind stress at the surface. And if I multiply this one by rho naught, that would be the northward component of the wind stress at the surface. So I could eliminate these two terms in favor of the applied wind stress at the surface of the ocean. So the surface boundary condition is that rho naught av du dz is equal to tau, the wind stress, in the x direction, and then rho naught also av dv dz is equal to tau y wind. So then I can eliminate these two terms. Now at the bottom of the ocean, I also could have stress because of friction at the bottom of the ocean. And here we're just going to take an ad hoc parameterization. We're going to assume that as the current rubs against the bottom, it is being, the friction is to bring it back towards 0, the speed at the bottom of the ocean. So at the bottom, so this is the surface for the bottom boundary condition, we're going to assume that minus, av du dz is equal to r times u. So just proportional to the depth integrated current. this thing here is proportional, the friction is proportional to u, and the proportionality constant is r, and we're going to pick r. R is going to be a number that's on the order of 10 to the minus 6, 1 over seconds. So that's kind of a scale for the friction we can use. But we can try different values of r when we solve the mathematical model. But this is what's known as a Rayleigh drag, and it just says that the faster you go, the more frictional forces there is, and we just take it proportional. So it's the simplest possible model we can use. And we'll do the same thing for the y component. We'll say that, let me erase this and write the other one. AV dV dz is equal to RV, where R 10 to the minus 6 per second. Okay, so if I do those, then I can now replace here the surface wind stress. So I will just put in tau x divided by rho naught. And same thing for this one, using this equation, I guess just tau y. Oh, that's wind. Wind. And same thing here. Tau y, wind divided by rho naught. Using this equation. And then at the bottom, this just becomes minus r times u. And this one just becomes minus r times v. All right, so these are my depth integrated momentum equations, assuming that the inertial terms are small and that the flow is pretty steady so that the time derivatives are also small. And now we still have these depth integrated pressure gradient terms, these pressure forces, and we want to eliminate those. And the way we will eliminate them is by forming what's called the vorticity equation. So we're going to take the x derivative of the second equation and subtract from it the y derivative of the top equation. And this will give us a mixed partial derivative with respect to p, from which we'll subtract again, oh, I forgot the minus signs here, minus, from which we'll subtract the mixed partial derivative of this one, and these two terms will vanish when I do d by dy of this minus d by dy of that equation. So let's do those calculation. So erasing all these boundary conditions here. And forming the vorticity equation. So if I call this equation 1 and this equation 2, I'm going to do d by dy of 2 minus d by dx of 1. And that's going to give me f times du dx plus, or sorry, minus plus f times dv dy. However, f here is a function of latitude, right? So f increases as we go northward, or decreases as we go southward. So I'll also have to keep a plus and v, or a plus df dy times v, right? Because v varies with latitude. If you recall, f, this is the Earth, this is omega, the spin axis of the Earth, or 2 omega, and if this is the equator, this is latitude phi, then f is the vertical component of the 2 omega vector. So if this is 2 omega, the projection on here, this here is f. And so you can see that if you're at the North Pole, f and omega are perpendicular to each other, but as you get towards the equator, f is perpendicular to 2 omega, so that f vanishes. In other words, the vertical vector is perpendicular to omega, so f vanishes. And so when we're going to keep this derivative because our y coordinate is pointing northward, so we will retain that one. So in fact, let's write out df dy, which is the same thing as 1 over a for the radius of the Earth, times df d phi, right? A times phi, that's arc length around the surface of the Earth, which is our y coordinate, and we're going to define this as beta. And this is equal to 2 times 10 to the minus 11, roughly 1 over meters second. And so we can replace this here by just beta. That's beta v. All right, so we've taken care of the derivatives, y derivative of this minus y derivative of this one. And now this one, right? These ones will cancel. This will be d2p dy dx. This will be d2p dx dy. We can interchange the order, so these vanish. And then we're left with this one, which will be plus AH, this horizontal Laplacian term, times dv dx minus du dy. And we'll also get this term, the d by d1, well, let's just write it out, 1 over rho naught plus d by dx of tau y, the y component of the wind, minus d by dy of tau x wind. And then the last one, minus r times dv dx minus du dy. All right, so this is now, this equation over here is the vorticity equation that we will use to solve for the gyre. We can make some more simplification here. Let's do those extra little simplifications before we finish up. Erasing all this. Right, this term here, f times du dx plus f times dv dy, well, this term vanishes, right? Remember that from the depth integrated continuity equation, we know that this is equal to 0. So these two terms actually vanish, right? Because it's just f times this is 0. So we can eliminate these terms. And now we have our vorticity equation. Let me rewrite out nicely. So beta v. Wait a minute, where's the equal? I need an equal sign here, right? Equals AH del squared horizontal, and this term is the vorticity. dv dx minus du dy, that's the vertical component of vorticity. It's the tendency of the fluid to swirl. So this is the vorticity, dv dx minus du dy plus 1 over rho naught. And this is also the vertical component of the curl of the wind. So this is k, I just write it like this, curl tau. Tau vector, the horizontal vector for the wind. And the last one is minus r times the vorticity again, dv dx minus du dy. So this is our vorticity equation. And before we solve it on the computer, we're going to do one more approximation, and we're going to assume that these horizontal divergence of the eddy stresses, or this horizontal diffusion of vorticity, is small compared to the wind and the bottom friction. And so we're going to neglect that one. So that's just an approximation. We may have, if we have a chance, we may come back and retain this term and solve the model with this equation also. It's just much simpler as a first cut to just neglect this term. So we're going to assume this is small. So this is small, assumed small compared to minus r dv dx minus du dy. So compare, we like this compared to that one in the model. Okay, what's the physics behind it? So what happens is, you could think of the curl of the wind, so that's the horizontal shear of the wind. We'll put in vorticity. We'll cause the fluid to try to shear, and we will see that almost everywhere in the ocean that this term is going to be small. This one is assumed small, and there'll be a balance between the input of the wind and this planetary, this beta v term. In other words, the wind is going to put in a negative vorticity in the ocean, which is going to cause the fluid not to spin faster, but to drift southward. So instead of spinning faster, it's going to adjust its latitude so that the planetary vorticity is less and less aligned with the Earth's spin axis. So there's two ways in which the fluid can have vorticity. One is it can turn with the Earth, that's called the planetary vorticity, and the other one is it can turn relative to the Earth, that's called the relative vorticity. So this quantity here, or this one, is the relative vorticity, and this one here comes in from the variation of the planetary vorticity as the fluid flows southward, so it will decrease. So we will have our model being a balance of these terms in the interior, and then in the western boundary current, the currents get very fast, and this term will then become important, and in the western boundary there'll be a balance between this term and this term. All right, that's all quite abstract. I think when we see the solutions it will become more clear what's going on. All right, there's one more thing I want to introduce before we go to the computer, and that's this concept of a stream function. So because we know that du dx plus dv dy is equal to 0, this is a horizontally non-divergent flow. That means that not any velocity field can be used, only those that have no divergence horizontally. And an easy way to construct a flow field that is horizontally non-divergent is to introduce what's called a stream function. So we'll let psi, which is a function of only x and y, be the stream function. Such that u is equal to minus d by dy of the stream function, and v is equal to, oh, this is capital U, sorry, u and big V is equal to is equal to partial derivative of psi with respect to x. So if I have a stream function and I take its y derivative, negative of the y derivative, I get u, and if I have a stream function I do the x derivative, I get v. And you can see now that if I compute du dx plus dv dy, I'll get the second mixed partial of psi with respect to y and x. And this one, if I do the x derivative, I'll get, sorry, if I do the y derivative, this one I'll get the second partial derivative of xy, so that when I stick it in here, this flow field defined this way automatically satisfies the fact that the flow is horizontally non-divergent. And I can also rewrite the vorticity, the relative vorticity, in terms of the stream function. So if I substitute in these values into the relative vorticity, what I get in the final equation is beta d by dx of psi, right? I've replaced v by this. This term we're pretending it's small is equal to 1 over rho naught curl of tau for the wind minus r. And if I do dv dx, that's going to be the second derivative of psi with respect to x. So this is d2 psi dx squared. And then the d by dy derivative of this one will become minus becomes a plus d2 psi dy squared. And so this is again our friend now, the horizontal Laplacian operator. So we can just replace this, right? Second derivative with respect to x plus second derivative with respect to y with simply this expression. All right, so this is our new equation down here. And the nice thing is now this is a partial differential equation. It's got derivative with respect to y and derivative with respect to x inside this Laplacian. Partial differential equation, but it's only in one variable. So instead of having two variables, both components of the horizontal velocity, u and v, we only need to solve for one field, psi, and once we have this field, we can take its derivatives to recover the velocity field. So that makes the solution of the problem much simpler. So this will be our linearized, no nonlinear terms. We dropped them when we dropped the inertial term because the Rossby number is small. The linearized vorticity bounds for a subtropical gyre. And from this mathematical expression, we will solve it on the computer and get pictures of the stream function and the currents in the gyre.